What are we talking about today, Adam? What do you have for the viewers? What do they
Yes.
want?
So we are talking about channels, continuing our discussion of streams. So we were going to talk about Quill, but just given some timing issues, we're going to be picking that up with Alex another time. So this is part 3 in our series on streams. And we, in the first session, we developed our own model of streams as these incremental producers of values. And we essentially modeled a stream as this effectual iterator. Let me see if I can find our, so we modeled a stream as this thing where we were able to open a managed scope, which might involve some kind of resources. So think about opening a file. And then each time we wanted more elements from the stream, we could think about this as a pull effect, that we could run this effect multiple times, and each time it would either give us a value, or in the real Z streams, a chunk of values, or it would give us an error message, or it would give us this none to signal that the stream was over. And so we built that up, and we built this intuition of a stream as incrementally producing values. And we were able to transform those stream values. We were able to perform some effects with those stream values. And so we eventually got to the point where we were able to load from a file and create this like stream that would incrementally read from the file. And then in our second session on streams, we added the concept of a sink. And we saw this idea that a sink was kind of the dual of a stream, whereas a stream from nothing or from something like a file or just an iterator just produces a bunch of values. A sink consumes a bunch of values to produce one summary value. And so we had a representation here that was in some ways similar to the one that we had for streams, where we again had this managed scope we could open, which could represent, say, a file that we were going to write to this time. But then this time, instead of being a function that just effectually produced values, this was a function that effectually consumed values. And so we said, given a chunk of inputs, we're going to perform this ZIO effect. And the way we encoded it last time, we said it's going to produce this option of O, where the semantics were this: if it produces a sum of O, then that means that the sink is done consuming values and it's produced this summary value. And if it's none, then it means that the sink wants more inputs. It's like the Cookie Monster. It's like more, feed me more elements before I'm ready to produce my summary value. So we got those two things, and by the end of the last session, we were able to already do some relatively sophisticated stuff, where we were able to combine these two sinks that would both consume stream inputs in parallel. And we were able to use that to implement this functionality where we read incrementally from one file, and then we both in parallel wrote incrementally to a different file, as well as printed those things that we were writing to the console. So there's definitely more we could do around more complex stream operators, but hopefully from the last two sessions, people have a good understanding of what's actually pretty close to the way that streams were and sinks were encoded in ZIO 1.0. And so definitely, if people have questions, we can recap on that. But the goal of this session is to fast forward from ZIO 1.0 to ZIO 2.0, because ZIO 2 introduces a new encoding of both streams and sinks based on this concept of a channel. And this is something I think we've talked about a little bit in different forums as this unification of streams and sinks. And Itamar gave a really great talk introducing this concept at ZIO World, but I think necessarily that was a relatively shorter conference talk where it was focused a little bit more on both introducing the concept and then some of the high level, the performance benefits and so on, but maybe not so much building up the intuition from scratch. And so the goal for this session would be for folks who are either using ZIO or interested in ZIO, and you're on ZIO 1 and okay, you're looking forward to ZIO 2, you know there's this channel thing, to give you more of an intuition from the ground up like we usually do of like, what is a channel? How did we get here? And hopefully by the end we'll build up to some of the benefits. And we're not going to do the exact encoding that is used in ZIO 2 because that's a declarative encoding. So it's like ZIO itself, where if you did our ZIO from scratch series, there are a bunch of just like data types that describe the different fundamental operators that are just data types. And then there's what's called in ZIO 2 the channel executor that goes through and executes those, just like the ZIO runtime executes a ZIO effect. And we'll try to at the end talk about why we did it that way and some of the benefits of that. But I think implementing that channel executor from scratch is beyond the scope of what we can do in just a symposium. So we're going to be doing a more executable encoding of that will hopefully give you the intuition of how we got to channels and how channels work without requiring quite as much buildup to create that interpreter. So hopefully that is helpful for people.
I'm very excited. Well, I'm very excited, but yeah, I think if anyone remembers from or saw the ZIO from scratch series, translating from the sort of executable / hybrid approach to the fully declarative definitely obscures some things. So I think keep it pedagogical, and then we could always, translate mentally later. Or that could be an exercise for the reader.
All right, so let's start. And so the way I would think about this almost initially is it's almost like we're doing, like we're particle physicists here, and we've got these different particles we're seeing, and we're wondering, is there a more fundamental building block for them? And we'll get later to like more practical benefits, but we could almost just initially approach this as a intellectual exercise of like, we've got these two things that we like see in the world of these streams and sinks, and we're trying to understand them more deeply and ask, is there a more fundamental building block that both these things are examples of, or are these both two distinct fundamental building blocks? And that's what the shape of this reality of this streaming world looks like.
And physicists do that by smashing things together, right? So we should probably smash them together.
We need a data type collider. We just throw type parameters together and we see what type parameters come out.
Yeah.
So to recap the types we had before, we had this Z stream we defined, and we said this was had an REA, and it had this, there we called it this pull method. And this pull was this Z managed RE ZIO R option E. And then we actually didn't do the chunk version, but this is like what the actual one in ZIO 1.0 looks like. So that's what a Z stream is. And then we had this Z sync. And oh, I'm sorry, let me give us the variance annotations there. And so this had an E, it took an input, it produced an output. And I think partly because I have exactly the same thing above, Copilot can recognize this thing. And so, okay, this is kind of what these two different things look like. And so let's start just playing with them and playing with the types a little bit and thinking about how we can, intuitively looking at this, it seems like there's some similarity here of, I think we even called this push, like we can pull values from here. We have some idea of we either get values or we get this end signal. here we push values here, we possibly get this end signal. So like there feels like there's similarity here, but let's try to see how just first kind of maybe playing with labels and playing with exactly the way we just show these types, we can make that a little bit more clear. So the first thing is we can see, okay, commonality, both of these involve an environment. So let's make this even more clear. Let's just call this environment here. Okay, now looking at streams, we can say they have this error type. And if we wanted to be, if we're okay being a little bit more clear / verbose, we might call this the out error. That this is the stream can output an error of this type. And similarly, we might call this type, maybe again, let's be clear, let's call it the out element type. That this is the element that the stream produces. And so this makes pretty clear this idea that, okay, the stream is producing these values. Let's do one more thing here, which is, we talked before about the idea that this option thing and putting in the error channel was a little bit of an optimization, that we needed to signal the possibility that just the stream was done somehow. And we thought, well, we can represent that as either an option of the error or an option of the value. And this way, the happy path is a little bit cleaner. But right now, we're trying to think a little bit more just about the fundamental representation of this. So let's like kind of undo that optimization. And so we could say, looks like this. We just move the option back into the value channel. And then let's do one more thing here, which is, we know that an option is really a more specific kind of either, right? It's essentially an either with just this like unit or not meaningful value on the other side. So let's make that a little bit more explicit. And we really said we're using this other thing as this like done signal. So we could say that this is actually going to be an either. And we can kind of do these in any order we want, but maybe just for me right now, I'm going to put it here. And I'm going to give myself one more type parameter here for the outdone. And let's see, I think I just have slightly butchered this. I think. Yep. Okay. And we know in the typical stream case, this outdone is just going to be either unit or any. It's not a meaningful value. It's just the fact that we get a value at all that in this case is a right instead of a left is the way that the stream is signaling that it's done versus it's producing another value. So, okay, now we've got kind of this that requires environment like everything does, and it produces one of these three things. In fact, it can produce element, 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 and then at the end, it's either error or done. So, okay, that kind of makes sense. Let's try playing with the sync in the same way. So we can say here that this O value really represents the outdone value of the sync. We can say that this E here actually is a little bit split into two different E's here. But right now, let's just, why don't we call this the out error? And then this I, this is really, it's the in element, right? We feed multiple elements into the sync, and eventually it's going to produce this done value. So let's be a little more explicit about that. Let's call this the in element. Okay, so now we're done making all of these type parameters longer, and maybe I will do this just so it's a little bit easier for us to see this.
Nice.
And so if we just look at this, we start to see a little bit more of that, like the fundamental building blocks as we smash this thing together of both of these things use environment type, which makes sense. That's the environment's a fundamental part of ZIO. So yeah, it makes sense that all these different things can use the environment. Both of them have some kind of outdone value. In this case, it's not a meaningful value. In this case, it is. This one has these out error and out elem values. This one also has an out error, but this one has a in elem. And so if we just think of this, and again, I kind of like this like physics analogy of like that case, they're always looking for kind of the like, you know, the particle and the antiparticle. Like if we just looked at these, we'd say, well, it's kind of interesting that it seems like there are some things that are missing here. Like the environment always exists. Okay, that makes sense. There are these like, seems like three different things. There's an error, an elem, and a done. And we can have out versions of all of these. This says we can have an inversion of at least one of them. So logically, we kind of think, okay, well, that would indicate that maybe there's also a in error and a in done that we need somewhere to represent all of this. And we could also say, well, okay, we've got a pull and we've got a push. So what would it mean to combine those two and essentially have something that has both a pull and a push?
Smash them together.
And so that's basically the starting point for thinking about this channel. And so it's going to have all of those hypothesized type parameters. And so it's going to have an in error, it's going to have an in elem, it's going to have an in done, and it's going to have an out error. And that is definitely wrong. But right now, we'll just make this a question mark while we think about this. And do we, oh, I think we just need, oh, perfect. There we go, lovely. Okay, so conceptually, we could think about the channel as something that has both this pull and this push. And so something that both we could pull values from, as well as we could push values into. And so you could almost think about it like if you have, you think about you have some kind of like Java NIO, like asynchronous file channel or something, you can write to it and you can read from it. And so we've got to think a little bit about how we want to represent this. And so one way we might think about it is we're going to represent it just by having like a pull and a push. And so you could imagine kind of the pull looking like this and the push looking maybe something like this. But what we run into a little bit with that is that doesn't give us quite what we want, because it doesn't give us the pull and the push the ability to interact with each other. Of when we're defining the pull, all we can do is we can pull. We can't say what we want to do with the other side. And so this kind of forces us just to like every operator just has to have like an internal queue. Ends up being a little bit less interesting. But a way we can change that around is we can think of a channel as something that we can pull from as long as we give it the upstream that we want the channel to process. So let's play a little bit with what that would look like. So if we first do, let's focus first on just the stream half of the channel, because I think the stream is probably more intuitive for most of us. So the stream part of the channel is still, we're still going to want it to be a Z managed because we're going to want to be able to use the environment. And that's going to be able to fail. And we're still going to have this pull-like thing here. But now this last type is going to be a little bit more like what we had in our representation up here. And I'm gonna not use the chunking at the channel level. I'm gonna reintroduce the chunking a little bit later, but right now I'm not gonna introduce chunking here. And so let's see, ZIO, right? That. Okay, so this we could think of, I mean, this is basically just this minus the chunking. So this we could think of as the like stream half of the channel. So then we have this question.
We have a quick question, actually, which is that Phil Allen asks, Indun has changed its sign, anticipating something. Because I think before there was no Indun, actually, I think.
Right, Indun didn't exist before. Indun was something that we, in our physicist hats, we hypothesized exists because we saw outdone and we saw that we had an in version of one thing. So we hypothesized that there would be a in version of all the things. So yeah, it hasn't changed its sign. It just really has the expected sign of if the outdone was positive, the indone is negative. Does that answer that question?
Mm-hmm.
Okay. Okay, so then we're going to say, okay, we need a upstream to do this. So this is saying we need the ability to pull from our upstream. And so that, let's just start playing with this. So that we could start by representing as this is going to be a IO that is going to either fail with an in error or is going to succeed with, and we're doing it as a in LM and an in done. So this we could think of as the upstream. So a channel is now saying, if you give me an upstream, then I can go ahead and you can pull from me, right? If you give me the upstream, then you're going to be able to pull from me. And I'm going to perform my own internal logic of when I want to pull from the upstream or what I'm going to do. And then I'm going to eventually give you back the value that you're pulling from. And I think here, just like we allowed this thing to be managed, we're going to want to allow the upstream itself to be a managed resource.
Ooh. Tricky.
And you can see we're adding some complexity here. And I mean, this is part of one of the reasons that this is not actually the way it's encoded, but I think this is going to give us the most accessible way to kind of work through what these things mean, develop an intuition for it.
And if this is confusing to anyone, just know that it's also confusing to me. So you're not alone. And I'm sure through examples, it'll make sense. And we'll be sure to break apart every aspect of it that is confusing.
Yeah, exactly. Exactly. We are definitely going to do that. Okay. So we've got this guy. And now let's start thinking about how we are going to recapture these simple things from this guy. So first, let's think about what a stream looks like here. So we have this lovely stream REA. Oops.
One quick question. That inner
Yeah.
manage doesn't have, Philip noticed that that did not have an environment, right? Should that have ENV as well, or is that for now we could leave it as any?
Well, yeah, so that's a little bit intentional on both of these, because if we do this,
it's the wrong flip. Yeah.
Particularly, I think we may actually be okay with, well, okay, hold on. This one.
Yeah, Z.
Yeah. So first give it the Z. And now we're going to get a message that this occurs here. So I think we need to get rid of both of these.
Yeah, because they're both on the same side. Yeah, every time you're on the left-hand side of a function arrow, the variance flips, which is it works through it if you think about it real hard, but it can just let Scala yell at you and then trust it. But yeah, it flipped because we're now on the left-hand side of that arrow there. Like, oh, I'm not pointing on the right thing. Here.
Yep. And we'll see later why that's actually not a problem, but essentially the fact that we have this outer manage means we can always access the environment here, and then we can provide it here if we need it. So that's not ultimately going to be kind of a problem for us.
Cool.
Okay, so let's then play with a Z stream. And so in this world, a Z stream just is a certain kind of channel. And let's think about what kind of channel it is. It's actually not that kind of channel. So it's a channel that needs environment. Right now, I'll just put questions here for a sec. So we said before a stream was, it produced values. It just produced values kind of out of nothing. It didn't require any input. It just produced values. So what that means is that all three of these parameters can just be any. That the stream is just going to produce values itself without using any input. So it doesn't care what these inputs are. And then its out error type is just going to be this E type. And the out element type this time can be a chunk of A's. So we'll kind of reintroduce the chunking at this level here. And then this type, this outdone type, this is essentially that like none case of unit. So it's not a meaningful, like there's no meaningful value here, but just the fact that like there could be some value at all is meaningful. So here, I'm just going to use any here. And we maybe use unit, we could use any. I think any is going to work like slightly better with variance. So what this is saying then is this channel this stream channel doesn't require any input. And every time we pull from it, it's either going to give us a chunk of A's, or eventually it's going to either fail with an E to indicate that there's a failure, or it's just going to give us this any, this essentially write of any, to say, okay, I'm done. And then we're going to know that we're done with this stream. Does that make sense so far?
I believe so. We have a couple of questions, which is that, okay, one is asking, my question is, as you compose channels, is the end required for the whole thing allowed to get more specific compared to the upstream part? And I think the answer there, it sort of depends on specifics. I think we'll take a look as we maybe write some examples of these, but you can always, because it's contravariant, through composition will automatically narrow. It's just like in ZIOs, right? When you have one effect that requires a user service, another that requires a database, if you zip them together, it will sort of refine the environment and find the common subtype, which is and database and user service. So that'll happen with streams as well. So you can specify more, and it'll automatically sort of coalesce to be the full intersection because of the contravariants. And there's another question, which is in err and in done are all contravariant. Why any and not nothing? Why any and not nothing?
Well, that would mean that the channel could never be run. So that's not going to be very helpful to us, because then we're just never going to, right? That means the channel's looking for an input that can't possibly ever exist.
Yes,
so that's gonna result in sadness for us.
Yeah, any is sort of the one that you want to go for as the default unconstrained for contravariant types, right? So whereas nothing is the subtype of anything, of any other type, and therefore in the covariant world, nothing is still the subtype of anything. So you could, you know, any is the opposite. I don't know. There's probably a better way of saying that. I have a brain freeze now because I drank my smoothie too quickly. And we have
okay.
yeah, there we go. Okay. Oh, and a helpful comment here, which is the input type, the contravariant type is a requirement. The output type is for the expectations. Requirements must have a minimum expectation. The more you know, the more you expect of a type, and the less you can accept. Well, this is a great little thing. We should put this on something, on a tombstone. That's great. Anyway, Polaris, thank you for that.
Yeah,
I will post this.
That's pretty cool.
So lovely thing for anyone. But anyhow, cool. But I think we made it through the comments.
Excellent. And I think I'm just gonna see. I think I'm gonna play with this slightly. Let's see. I think I'm gonna give, yeah. So I'm gonna play with this slightly because I think I want to pull this outside of here. So I think this is going to be a managed in air of a IO. And let's see, is that happy? And then this is going to be, oh, this is going to be just a managed. Yeah, this is managed.
And sorry, what is
so I'm just clarifying this a little more. So this is basically, you give me the upstream you want to pull from, and I will give you something that you can open and then pull from yourself. Right, so think as this is the upstream. So a channel says, you give me an upstream that I can pull from, and I'm going to give you essentially a stream. This is really the same representation of a stream we had before.
Okay.
So let's try implementing a couple of things with this and kind of see how we can recover some of the same functionality we had before in this admittedly a little bit more abstract world of these channels here. So I think the first thing that we implemented when we were doing these streams is we implemented this from Iterator Operator. Yeah, you can try to make that. Oh, that's a nice way to, yeah.
So yeah, special request from Naveed. New line, please.
I think a good thought. Okay, so the from iterator is going to give us a Z stream, any nothing A. And so say, okay, well, how are we going to implement that? And well, we know the Z stream is a channel. So the first thing we can do is we can just say, this is going to be Z stream. And then This is going to be Z channel. And so what are we going to put in here? And so the Z channel is something that takes an upstream and produces something that we can pull from. So the first thing we can do is we can put upstream here. So this is, if we look at this type signature, this is basically very similar to the signature of the old stream we were looking at. So we get a upstream source, essentially, that we can open in this context of the managed, and that we can then pull from. And our job now is to essentially return a new stream. Now, the nature of being a stream as opposed to a more general channel is we don't actually have some input. So I think the first thing I'm gonna do here is I'm actually just gonna, maybe I'll copy this for a sec. And I'm actually gonna implement this at the level of this channel constructor. And I'll come back to this in one sec. But right now, I'm just gonna delegate to the channel here. So I'm just gonna say this is Z stream, and I'm gonna just say Z channel dot from iterator. I'm gonna say from iterator dot chunk iterator, because, and maybe I'll give this a chunk size that we'll initially just say is gonna be 1. And I'll pass in the chunk size here. And so at the channel level, now I'm going to implement this from iterator chunk thing. And it's going to give me a channel. And so this channel is not going to need any environment. It's not going to need any input. It can't fail. It's going to give me a chunk of A as element type, and it's not going to have any useful done value. I don't need those two. So I think it should be compiling here. Let's see, why is this not happy? From iterator chunk is not a, oh, I didn't put it on the companion object because I was silly. So I should do that. Let me copy this over. Oops. Okay, now it should be happy. Okay, so
I'm gonna move this down here just so we can get it.
Yeah. That's that seems like a good idea.
Okay.
Yay. So because we're not using the upstream at all here, I'm just gonna put it aside here. And so then all I need to do is I need to return this Z managed effect here. And so here I could say Z managed dot succeed with the iterator. And then I could map it with the iterator. And just because we have this chunk size thing here, I'm gonna just use this grouped operator on the iterator to take care of that for me. So now, well, I guess that is grouped iterator, but so now this basically every time I pull from it, it's going to give me a group of values of this size if possible. And so here, then, so this, remember, just like in the previous stream encoding, this corresponds to kind of opening the stream or opening the channel. So this is the action we do initially before we pull at all. And then every time we pull, we can just do ZIO.succeed, iterator.hasNext, and we can flat map that. And we'll call this B. And we'll say, so if B, if it has next, then we can succeed. And the way we want to succeed here is we want to succeed with a left of elements to indicate that we've got more values. So we'll succeed with a left, and this will be chunk dot from, I think this is iterable because we did that grouped iterator thing. And otherwise we'll succeed with a write. And we can just use unit here because unit is any. It's kind of an idiomatic value. And maybe format this a little bit. Sure. Good. Okay. Does that make sense?
Yeah. I mean, obviously, it's a lot of nesting, but I mean, and just to maybe a simple. So just to sort of clarify, right? So at every step here, we're wrapping things inside of succeed. Well, first of all, we need to return a managed. I mean, one could just maybe just as a slight rewriting, just to, which we don't want to do, but just to sort of also explain, we could have done something like this: just wrap this all inside of a Z managed, right? And then just done iterator.groups.map iterator, and then if iterator.has next, we could have then done these two sort of cases of this, right? So the ZIO.succeed on one side and the ZIO. And then else the right, right? That inner bit, I guess. But in order to be safe, right, at every sort of side affecting stage, like asking about calling has next and wrapping the grouped here, we have to be careful that that does not blow up, because the iterator, which is a lazy parameter by name parameter, we don't know how the user defined that. It could throw, and we want to catch that in ZIO and handle that, and let people, catch defects and whatnot. And same with iterator has next. That's iterator is a side effect thing. We don't know how that's implemented. The user could have made their own iterator, and it could be faulty, and it could blow up. So that's kind of the point of that. And so it can obscure a little bit of the logic. But yeah, I think the logic makes perfect sense.
Yeah, and I think the other way I would think about it is the managed is like what you allocate when you start the stream or this channel in this case. And then the ZIO is what you do every time you pull. So when we start the channel, we capture the iterator and we group it up. And then every time we pull, we see if it has next and we take that value.
Yeah, you're using that iterator. Oh yeah. And I think what helped a lot with the other episodes was in running them, right? So this is part of it. The definition is only half, though. When you finally execute them, you sort of get a fuller picture. So I'm sure we're going to do that soon.
Exactly. Okay, so that's what it would look like if we implement creating a stream. And we can create more. We could create the streams that read from files. Then this zmanage would do more real stuff. But I think we can see from this how we can create a stream that produces some values. Let's also look at how we can implement a stream operator here. So a really simple one that we did before was we had map. And we said, okay, I should be able to map over the streams and just change its element types. And so just like before, we're going to implement this on the channel. And because the channel has all these different type parameters, there are going to be like different variants of these. So you can imagine we can map over the elements. We can map over the done value. We could map error like we do with ZIO. But right now, we want to transform the elements. So we could implement something called map elem. That's going to have some out elem2. And it's going to have all the same, wow, this is, go Copilot. So it's going to have all the same type parameters, except it's going to have the out element type changed. And so this one we could think of as being the channel. And so we have some upstream. Oops. I think maybe I have one extra. And so all I'm going to do is I'm going to run myself with whatever upstream I'm given. And then I'm going to map. And I mean, actually, this is not bad. I mean, I could just do map myself, but this is maybe a little bit more clear. Let's just see what we've got going on here. Oh, we need one more map. Actually, yeah, I think maybe we'll just do it. So we've got lots of things we need to map inside. Basically, we map between these different things. And then I think we need one more here. There we go. So what it means to map over the channel is just whatever upstream we give it, that's going to produce a new thing we can pull from. And every time we emit an element, we're just going to transform it with that function. And so we're just delegating a lot to the map on ZManage and the map on ZIO, but we're basically just transforming each of those elements.
So yeah, so far, really, this is, I think, almost essentially our implementation of map on the other thing, except we didn't have to call a function to get the managed back. We just sort of had it. And then there wasn't a second managed inside. But all right, so that makes sense.
Right, and so far we haven't, to exactly that point, we haven't really been using the upstream because the stream that we implemented, kind of its defining feature is it doesn't need an upstream. It kind of is its own source. So let's now play with the Z-sync a little bit and see how we would use that. So the Z-sync is going to have an R, and then it's actually going to end up, we'll see, it's going to take two error types, which maybe for a lack of a better term, I'll call E in and E out. And then it's going to have that in type, and it's going to have an out type. And so it's also going to be a channel. And I'll just give myself question marks here so it's easier to see, and probably in a sec you'll move it down there, which is nicer. I think I'm just missing one or two of these. Okay, so what are these types for the Z-sync? So clearly the environment's like an easy one. So this next one is the in error. And so that'll be this EN. So this is the type of errors that you can give to this sync, because maybe there are some errors that the sync can't handle. Oops. Oh, nice. Yeah, perfect.
That's not really helpful, but yeah, I'll add
well,
these.
No. The documentation is helpful. Just I think it was. Yeah. Okay. So we've got an in error. Then we've got the in elem, and that's that I. We don't really have a useful in done value here because the in done just is going to signal like, hey, the upstream has no more values to give you. So that'll be any. And then the E out here is going to be this E out. And in this case, the elem type is going to be nothing, because we're not going to produce anything until we produce a summary value. And then the outdone case is going to be this O here. And so let's think about how we would implement a one of these channel constructors here. So one of the ones that we did before was this run collect one. That's just going to take everything and just collect it into a chunk, right? That was one of the ones that we like implemented, I think, at the beginning for just debugging purposes, because that was, okay, we're gonna see all the inputs. So what would that look like? So we're just gonna say run collect. And so this is going to be a Z-sync. Doesn't require any environment. We're actually gonna wanna give it, just like we kind of have the A parameter just for the type of values that we're gonna collect, we're gonna have an E here. So we're gonna say, if this thing can fail with an E, then we can also potentially fail with that same E. We're gonna accept inputs of type A, and our summary value is gonna be a chunk of A. Does that make sense?
Yeah, very much. So this, yeah, because this is taking values of A and returning eventually chunks of A. And
Exactly.
yeah, I can fit, and it has no requirements currently. So yep, that makes sense to me.
Okay, so let's try to implement this. So we know a Z-sync is going to be some kind of channel. So I've got to create this channel. And every time we create a channel, we get an upstream. So what does it mean if we have this upstream to collect all of its values? Well, the first thing we would have to do is we have to map over it to get what we could call the pull, just like we did in, oops, I think we got, I think we got maybe too many of these. Let's see if that compile. Okay, so now this pull is this effect that is either going to fail with an error or give us a value or a done signal every time we pull from it. So what would it mean to collect all of the values from this thing? Well, we might create some kind of recursive helper here that's just going to build up this chunk for us. So we're going to maintain this chunk as an accumulator, and eventually we're going to return an IO of an E, and then we know we're supposed to return either a chunk of A. Well, no, I think here, what are we? We said we are supposed to return either nothing, because that's our element type, or a chunk of A, which basically says, in this case, in our representation so far, we can't have leftovers. If we had leftovers, that would be what this nothing type was. But I think we've already got enough complexity here. We do not need leftovers. So then we could say, okay, we're going to start looping with the empty chunk. And then here, we could say we're going to pull, and we're going to flat map on the pull. And we are going to either get a left that has a chunk, or we'll get a right that just has it. So if we've been pulling from the upstream and the upstream tells us that it's done, then we're done, because we're supposed to collect all, we've like collected all the values. So in this case, we can just succeed with our accumulator. If we've got a left here, then
we would loop again. I see.
Right.
Sorry.
No, you're fine. Right. So we're going to loop again, and we're just going to add the new chunk that we got from the latest pull onto the accumulator we've been maintaining.
Yes.
And I think let's see. I think we haven't specialized this for chunk yet. So I'm going to go up here, and I'm going to say this always gets a chunk of input. So we'll have chunking at the stream and the sync level, but not at the channel level because the channel is more general. So we could think of this as just like draining the channel, right? We just keep pulling from our upstream until we've got a value.
Yeah, and then just putting it in there. That's nice. I mean, this is also pretty similar to what we did in the stream section. Yeah, okay.
Yeah, the difference is really just giving ourselves this reference to the upstream.
Yeah, but we haven't really utilized it yet. I'm guessing this is more the sync aspect is going to utilize that a little more.
Well, we've used it right here because we're pulling from the upstream every time.
Oh, that's true. We're mapping over the existing upstream. Oh, and this is a sync in a way.
Okay. Well, this is a sync in every possible way. Yeah.
Yeah. Oh, dear goodness gracious! I'm so out of it. Yes.
No.
Yes. Of course. So yeah. Yes. All right. So in the previously in our first iteration, in I think episode 1, before we got to syncs, we defined run collect as
a stream operator, I think.
As a special, either is an operator, right? As an operator, yes. And then we were able to abstract it into a sync, and now the sync version of a Z channel uses the upstream. So, okay. And the ones and yes, and so the constructors for Z channels don't touch the upstream, obviously. Looks like
some of them do, because I mean this one does touch the upstream.
Oh, that's true. This is also a stream constructor. Yeah. Okay. Yeah. A little trickier, but yes, I'm interested to see how this what patterns emerge as we implement some more operators.
So I think what we could say is stream constructors aren't going to touch the upstream. Like, so this was essentially a stream constructor. It doesn't use the upstream, but this one does use the upstream. So, okay. So now we've got a stream and a sync. So I think to your point, let's think about how we could get to a point where we can put these together and run something so we can start kind of making this a little bit more real. So there
is a bit of a discussion just about, I think I linked to we had an old video on variance, if sort of the any versus thing sort of tangent is confusing. However, perhaps it could be interesting just to sort of briefly talk about, also there's this sort of a mention in the chat of someone referred to sort of any to nothing as being the most, the broadest sort of method type.
Give me anything and I'll throw it in the garbage can. Yep.
Yes, but then some people responded saying, well, any to any is actually feels like the most broad thing, and it depends on how you look at it, because yes, if you have a function from any to any, you can call it and what have you. Any to nothing, you actually cannot define that necessarily. I guess unless you accept, you couldn't define this because nothing has no values. That's kind of the magical thing about nothing. Nothing
you can't produce a value of type nothing.
Yes, like Boolean has 2 values, right? True and false. Unit has 1 value. Unit. Nothing. No, nothing. There's nothing in there. I can't make a value there, which means that it can technically be the subtype of any other type. So nothing is a subtype of int. Why? Because prove it that it's not. Like, you're never going to get a nothing, so it may as well be a subtype of int. There's ex falso quadlibet sequitur quadlibet. That's a magical spell. That means from falsity follows anything. Yay. I learned that from Bartosz Milewski's book. But basically, it's like, yes, if you start with a lie, then nothing sort of represents this bottom type, which is also sort of false, 0. It is known by many names. The unholy one. And it is a subtype of anything. Why? Because there are no values of it. So you can say anything you want about it.
So it's sort of at the bottom of the type tree. It's beneath everything. Whereas any is at the top of the type hierarchy. It is a super type of literally anything else. So it goes, nothing's at the bottom, and then all the other types in strings, dog, animal, some other stuff. And at the very top is any, right? Now, why would any to nothing be considered a more broad as a type? Well, that's because in a function, the function type has its inputs and its output, and the output is covariant and the input is contravariant. And if we watch the variance lesson, this will make more sense. We don't have time to go into it deeply to also continue along with the complicated world of Z channels, but nothing is a subtype of anything. To be covariant means that the variance of the container matches the variance of the parameter there. So if nothing were here, then a container of nothing is also a subtype of a container of literally any other value, just as nothing is a container of anything. So the variance rules vary along with the container. Contravariance inverts that, such that if something is a supertype, so if we had the input takes a negative r here, then this would if r is a subtype of R2, then an input of R2 is actually a subtype of an input of R. So it flips it. It flips the sort of the subtyping relationship in relation to this container, which means that a function going from any to nothing will actually be a subtype of all other functions. So it's perhaps don't think of it in terms of being the broadest or most general, but it is sort of the least constrained in a way. And if you compose it with something else, this will get basically, this could be obliterated and widened or narrow perfectly into anything else, right? If you have two types of negative r going to plus a, and one of them is any to nothing, then it's sort of going to pick the bounds of the other thing. It's going to narrow it along the r and widen it along the a. So if one function needs an int, then that any will get obliterated and become an int. If the other function returns a string, the nothing will be obliterated and become a string. So that's kind of why it's useful for composition, because it really has no constraints. It accepts, it is a subtype of all other functions. It is the lowest you can go. And that's sort of why any is we use that when types are contravariant, even though it is slightly counterintuitive, because you're like, well, this doesn't need anything. So why not nothing then, right? Because the ZIO that doesn't need anything. So I want to say nothing because it needs nothing. But you should more think about it as that it has no constraints on the environment, and therefore it can accept any environment. It just doesn't care because it's not going to touch it. The variance video, I think we do a better job of explaining that. I hope that was a 3 to 5 minute regurgitation of some of the ideas, but hopefully that helped a little bit.
Yeah, I think takeaways are, think about minuses as inputs, pluses and outputs. Think about any as a value that's like a sentinel value that has no information, and nothing as a value that can't exist. So like if we think about these like streams and we wonder like, should this be any or nothing? Any here means we're saying this channel at some point can emit this value that could be anything, has no significance other than it is this value. If we said nothing, then we would be saying this is a channel that can never end. It always will produce more values, which is something else we could say and would be a well-defined thing to say, but it's definitely a different thing to say. Okay, so let's see, what happened to our map here? Oh, maybe we never implemented it. We implemented the Z channel map elem, so we can easily implement this as dot map elem. Parameter type.
I think we need to do channel, right?
Oh, channel. Thank you. Yep. Thank you. What?
Oh, we need to chunkify it.
Yeah, or we can just map it again. Yeah, map it. Yeah. Yeah. Okay, great. Right, and we can have another like map chunk that does that. Okay, so we've got streams, we've got sinks, we've got at least one fundamental constructor for both of them. We're kind of trying to build up to the like, have a stream, have a sink, run them together, see some numbers output, and feel like, okay, these we're actually doing something here. So I'm sorry, go ahead.
Oh yes, now we need to compose them. Yay, plug them into each other.
Exactly. And so this is where I think things are going to start getting maybe a little bit nicer than in the old world. Because in the old world, when we wanted to run the stream and sync together, we kind of had to have this like a little bit like complicated logic where we created this other thing that kind of was like the manager that went back and forth between pulling them here. Versus here, we're going to be able to view that as an example of a more fundamental operator here. And so this, we kind of call the triple arrow, or you could think about it as like compose. But what this is going to do is it's going to say, if I got this channel that takes some inputs and produces some outputs, then I should be able to put it together with another channel here that is going to maybe require a little more constrained environment, right? To what Kit was saying before, maybe the first channel didn't need any environment, but this channel needs some kind of logging service or something. That's fine. This channel, its input type is going to be the output type of the first channel. So it's going to take the errors, the elements, and the done value the first channel produces. And then it's going to have its own out values. And we're going to call this maybe out error 2, out elem 2, and out done 2. And these are going to be completely unrelated. So this will be like, we might have one channel that takes in nothing and produces bytes, and we might have another channel that takes bytes and produces strings, and we can just put those two channels together. And so this is going to have, I'm sure we can make this not be so long. Yeah, exactly. So this will have out error 2, out elem 2, out done 2. Oops. And then this is going to produce a new channel that's going to require that possibly more constrained environment. And it's going to have the inputs of the first channel and the outputs of the second channel. And you could think about this as like function composition, right? Of like these, you could think of these channels in a way as like fancier, like incremental functions that like they can acquire resources and you can pull from them incrementally, but like ultimately like a channel like takes ins and produces outs. And so if you have one thing that takes ins and produces outs, and you have another thing that uses those outs and produces new outs, then you can plug those two things together.
I mean, that's the beauty of functional programming. I mean, it's, yes, with all the type parameters, you can become just overwhelmed and explode. But it's really just when you have types that look like functions, where you have a contravariant input and a covariant output, you can compose them like functions, and you get all of these particular operations and behaviors sort of for free. I mean, you need to implement them based on their own individual semantics, but you can expect certain things to exist. And then there's sort of like the normal boilerplate of dealing with, okay, we have these other variables that are riding along, like the error types and whatnot. But that's really just a matter of, you know, bookkeeping and tracking and putting them in the right places and potentially widening them based on when the compiler yells at you, or when you have been yelled at by the compiler enough times to anticipate and understand what those cases are.
Yeah, and I think the other thing is when you define things more generally like this, and you do it the right way, then you give yourself the ability to go back and like, stream looks exactly the same. Like if you're scared of these type parameters on Z channel, that's okay. Like you don't have to work with Z channel. Like Z stream has exactly the same type parameters you're used to. We'll try to hit at the end after we implement a little more on like why your life is going to still be better for this, even though you're not dealing with a Z channel directly. but we can have these things that are very general, and then we can specialize them. So we still just get to work with these nice things like the Z stream, and we have 3 type parameters versus 7 type parameters.
Yeah, and I'm sure by implementing things in this foundation, I guess you mentioned that at the end, we'll explore what this buys us beyond some sick satisfaction.
Yeah, so here we say, okay, we need to make a new channel here. And right now we know the way a channel is defined is it takes some upstream and it does something. And so here, if we like think about it a little bit, so we need to, so let's look at these types for a sec. So this upstream is an upstream that produces the inputs that the original one needed. And so you might say, well, like a very simplest thing we could do is we could say self.run upstream. But that's not going to work because that's going to give us the original outdones and not the new outdones. So we really need something like that.run self.run upstream. And then if we look at this, so look, compare these 2 type signatures. Maybe I'll just copy them here so they're a little bit easier for us to see. So we're pretty close here, but here is where we've got to kind of pay the price for what we talked about earlier with the environment type. So this thing here right now uses the environment, but per our signature, what we provide to run is not allowed to use the environment. So, you know, do we have to give up on everything? Is this a fundamental flaw? No. So what we can do here is this whole thing, when we call run, we're just getting a managed. So I can just do z manage.environment. We'll flatten out that and be better at typing. And then I can provide the environment here. Oh, and this I need to specify maybe. Okay, and so now if we look at our error message, we're a little bit closer. We just have one more thing to do, that we actually had the environment used in 2 places. We had it used in that like outer managed and the inner ZIO. So I'm just going to map to get access to that ZIO. And I'm going to provide it with the environment as well. And that compiles. And so this is actually pretty cool, and I think pretty like elegant when we think about it. Like, I mean, there's a little bit of boilerplate we added here with this like providing environment here, but like this is actually like a pretty like minimal way to say, like, the way we combine these 2 channels is we run the downstream, the most downstream channel, right? We run that channel, and the upstream we provide to it is the upstream we get by running the first channel. And then we're just doing a little bit of bookkeeping on the environment, but that's all we're saying here. And just with this, we've implemented this way of gluing together these 2 channels.
Yeah, and if we just to simple, I mean, so there's the environment stuff, but if you simplify that, right, like just to, sorry to copy paste again, but just in case that's some noise, we're basically creating a Z managed, ignoring the environment. Ignoring the environment. Well, that's just maps to provide
if we're ignoring the environment, we don't even need that. I mean, if we're ignoring the environment, it's just literally that.run self.run upstream.
Awesome.
Other than playing with the environment, that's all we're doing here. So it's pretty elegant.
Yeah.
So
that's not bad.
Okay, so let's undo that just so we kind of get back to compiling here. And I'll take this out. Okay, so now we've got this way of composing these things. So now let's go back to our problem of like, fundamentally what we want to do is we want to create some basic stream and we want to like run it to the sink, and then we want to like view the output. So let's re-implement on our old stream encoding, we had this run method that took some kind of sync and returned a ZIO. So how do we implement that in this new channel world? Well, so let's think about what type we need for our Z-sync here. So the Z-sync, I think, has 5 type parameters in this world. So 2, 3, 4, 5. Okay. So we'll play a little bit of just like type Tetris here, so as Kit would say. So we'll say the sync can use its own environment, and that maybe is a little bit more constrained than the environment of the stream itself. And so we'll need that additional environment. Then we'll say the next type parameter to the sync here is the error type that it accepts. So the error type that it accepts is going to be the error type that this stream outputs. So that'll be E. We'll say the sync can possibly fail with its own type of errors, which we'll call E2, which I think is the 3rd type parameter. Yep. It is going to consume elements of type A. It's got to consume what the stream produces. And it's going to produce some summary value that maybe we'll just call Z here. And so this is going to be able to fail with E2 and terminate with Z. Okay, let's make sure that works. All right, so let's now check out how nice this implementation can be. So here, we can do, so let's see what happens when we do self.channel and we type that channel to the sync. This isn't quite going to get what we need here, but look what we get here. So we found a channel that requires R1, and it can fail with an E2, and it can end with a Z, and it doesn't require any input.
We just need to delete those things. Just need to delete the that stuff, and then it's almost the same. It's got to delete it.
It's very close. So this is where we kind of need one more thing here, which is how do we actually run a channel? So so far we've implemented this pipe, this compose operator, or it's sometimes called pipe. We've implemented this map element. But let's implement one more operator here that actually executes a channel, right? That turns a channel back into a ZIO. And so this is going to require some implicit evidence, because when is it well defined to run a channel? When can, if I give you a channel, when can you just go ahead and run it?
When it has no input. I'll answer in unison with everyone else, I'm sure, at their own computers.
Exactly. So we can do
or
that.
Rather, when it accepts any input.
When it accepts any input, yeah. Exactly. So we'll say when any is a subtype of in error, and any is a subtype of in alum, and any is a subtype of in done. So basically, when we've got this channel that doesn't actually require any inputs, even though a channel in general could require inputs, this channel does not require any further input, then we can run it to a ZIO effect that is going to require the environment, that could fail with the out error. And then we have a little bit of this, we've got these 2 different things. So right now, I think we're just gonna say it's going to succeed with a chunk of the out elements. We're just gonna collect them all to a chunk then. There are other ways we could run it, but right now we'll just run it to kind of get all the values. And it's also gonna give us the outdone value if it succeeds. And Right, and I'm just gonna give myself a question, or oh, I think now I can say dot run drain and oh right, dot run drain, and then I can do that dot map blank dot 2. Okay, so now if I can just implement this run drain thing, we should be able to actually run our channels.
Oh yes, the run drain, of course. Ooh,
Yeah.
can I try by
Yeah.
speaking out loud and being silly? Okay. So, all right, everybody, let's try to do it. This is scary. Well, we probably have to look up and use our run method, right? Because that's really the only way we have of running ourselves now. So I'm going to look to this. And this is a method that takes a managed, but of the in elements, which I know are empty now, right? So I could probably just feed it, just ignore it completely, right? Do I give it a function or no?
You've got to give it something. So you've got to feed it something. Yeah, what can you feed it?
Okay, so it needs. Oh, so let me copy the signature down here so we can all look together.
Yeah.
No, that's not. There it is. Okay, it's on the wrong clipboard. There. Okay, let's see, everybody. What have we got? So, yeah, we've got to feed it this, right? So when writing these really crazy polymorphic functions or what have you, it's just, you know, there are a few tactics you can follow. One is if you have a function and you need the output, then you forget about the output. Your whole goal is now narrowed in on the input. And then if it's really complicated, don't worry about the insides. Check out the outside. We need to make a managed. Can we make a managed? Yeah, heck yeah, we can make a managed. We can construct them in all sorts of ways by doing managed. And then we could just, I think, put something in here or do from ZIO or something. So we can construct one of these. So what's inside of the managed? Well, it's technically a couple things. So it does take an in error, which we know is any. So maybe we could fail, but I don't think that would be correct. So you can rule out some options right away. So we want a managed of an IO of either in elem or in done. Well, we probably want to do the done one. So maybe I could just make a managed dot from ZIO. Oh no, I don't even want to manage from ZIO. I just want to manage dot succeed, where I inside of it have a ZIO dot succeed of probably a write, and in done is literally anything. So why don't I just put a unit in there? And then if I call this, well, that should work. And it's going to get me, oh, Z managed, thank you. And then this is going to get me my Z managed out. So, all right, I can do stuff with the Z managed. I can potentially, if I want to get a ZIO, one thing I can do is I can call use now, which is going to basically just turn it into a ZIO of the same types. And so I'm going to get a ZIO of another ZIO. And those have the same out end and everything. So I could probably flatten it to just nest it into a single ZIO of end, out error, and then in either of these two things. But one takes a chunk. So maybe that wasn't the right step because my goal is to get a chunk of these things. Mm-hmm.
So what you want to remember here is that once you run this thing, so you get this back, and remember that this gives you a scope. And within that, you can call this potentially multiple times. Each time, you're either going to get back an out elem, or you're going to get back an out done or an out error.
Yes. So sometimes if you're just following the types, as I just did, you can reach a dead end and realize, okay, that doesn't make any sense because I need a chunk of elements, and now I have to like wrap that in a chunk, right? Do something suspicious just to fill the type signature in a way that you feel like you're probably violating some semantics. So instead of doing use now, which technically gets us closer to our target goal, there's another one, which is use, which will give us access to the inside, which will be that ZIO effect. Okay, which is, I think we kind of called it the pull, and it sort of is the pull. So we'll call it pull. Great. And at this point, we need either both a chunk of out elements and an out done. So I'm just going to be silly right now and maybe make some a couple vars. So I'll have a builder for the elems, elem builder, because I need multiple of these, and then we can fix it up in ZIO later.
Yeah, maybe we could use another loop function like the before.
Oh yeah, sure. Oh, that's great. Yeah, I like loops. So yeah, we can have an accumulator then. I like it doing the functional style. It's probably even better. So we can accumulate our out elements. And what can we do? Well, we want to call pull. And then we want a flat map on it, probably. And we want to see what we have. So I'll say there's two options, right? It's going to be a left of some of the elements, right?
Left of the elements, exactly.
And how many will be in here? Just a single out element. Okay, so if it's a single out element, then we loop and we prepend this onto our chunk of accumulators, right? And then we loop again. We got an element. We got whatever that means. We got it. You don't even need to care at this point, as long as you know what the types are. And then if we're done, well, we're done. And therefore, we just want to sort of ZIO.succeed, taking our accumulator and zipping it up with our done element, I believe. And then we need a call loop, loop-de-loop. And we need to give it a type when you do these recursive things. And it has to be end, out, error. It has to be the same thing as above, right? And then a tuple of a chunk of out elements, and finally the done elements. So these out elements are the leftovers. So I think that might be something worth looking into. Does that not have, did I get that backwards?
Well, I think just since it's a chunk, it doesn't have the colon, and we don't have to do the whole reversing thing because we can just append to it because it's not
Totally.
like that.
And is this happy now? No, not quite.
Let's see.
It needs its chunk. It needs
Chunk
the chunk. Did it work? Yay, it worked. We did it.
Okay.
Cool.
And sorry, what were you saying about leftovers here?
So so we haven't really used them anywhere yet, and we didn't actually implement them last week. So it would be interesting. I mean, we don't have much time, but it would probably be interesting to talk about some use cases for them. But maybe we could do that next week or some other time in the future as well.
Yeah, I think that's definitely because let's try to get to having some.
Yeah, exactly.
Yeah, so let me create down here. I'm going to create an example, and I'll import channels.all. Oops. And this is going to extend ZIO app default because we're got ZIO 2.0 goodness. And then I'll say stream is going to be zstream from iterator. And this is now just a normal Scala iterator, 1, 2, 3, 4, 5. And so then I should be able to do val run is going to be stream.run zsync dot, I think we called this collect all. We call it collect all, or run, maybe we called it run. I guess we call it run collect. Maybe we should call it collect all. And then I'm going to take this whole thing, and I'm going to run drain. Oh, did we? What was the signature? Oh, I guess I built everything together into run. All right.
Yeah, into the run method.
Yeah. All right. Sorry. Yeah. I think. Okay. I think you could also like separate those out more, but yeah. Okay. So we'll do that, and then we'll just debug this so we can see what we get here. And I think we should be ready to at least try running this and see what we got. And this is an example. Look at that.
Whoa. All
so,
right.
I mean, admittedly, we did a lot of build up to take 5 existing numbers and output the same 5 numbers. But
well, can we map over it or yeah, we can map over it, right? We can map
should be able to map over it.
2. Yeah, that'll be pretty cool. Times 2, everybody.
There we go.
Amazing. And basically this is run is at this point just a simple composition of that
of the arrow operator. Right.
One drain at the end, right? Yeah.
And just we need to.
Oh, then you need to map over the results. Yeah, exactly. Yes, so that is why we still have this higher level run method to compose these subtypes. And generally, you're not going to, you can't run a stream multiple times.
Yeah. And now we
But
see we get that. Yeah.
cool.
Yeah.
All right. I mean, that's basically the implementation of run though. So
Yeah.
I like it.
Yeah. So I think we're getting time here. So maybe just to like summarize and give a little bit of just more context of all this. So hopefully you can see here how we actually understand, I think, a lot more about like what a stream and a sink are with this concept of a channel. And we kind of see how they really are both examples of this like more fundamental thing. In ZIO 2.0, it's more of declarative encoding versus executable encoding. But I think this is actually like a useful mental model of like a channel says, give me an upstream, and I'm going to give you something that you can pull from. And that gives us the ability to find these streams and sinks, but we can also define other things that are channels that don't necessarily fall into these two. So we could just have a channel that just like says, well, whatever bytes I get, I'm going to turn into strings, right? That would be like a decoder, or you could have an encoder of a channel, or you could have a channel that every time it gets an input, it emits that element as an output twice, or it gathers up some inputs and then it emits them as outputs. So channel is very flexible, and it lets us implement these things, but it also lets us implement other things that don't fit into just this like narrow world that now we can understand more, that we have this like more fundamental understanding. And it also allows us to do this in a way that's more performant, because for illustrative purposes here, we used all these like ZIOs and Z-managed, and we went through all these effects just because already this, kind of taking up the hour and a half. But if we just have one data type, just like we have one data type like ZIO, then we can have our own optimized executor. And we can use ZIO in that executor we want to, but we can have a lot of stream operators that maybe don't need to use ZIO, that maybe are just like transforming some like chunks where like we can avoid some of those costs of like going through the ZIO execution when we don't need to. So that's kind of some of the like how channels are working for you. But hopefully this gives you more of like a sense of channels fundamentally.
I'd also imagine that that environment bit, because that was a little awkward, right? When we did the compose operator, you had to call provided all the time, and then you're imagining, oh, well, that's doing all the ZIO stuff. We're getting the environment, we're looking it up, and we're providing it necessarily. If you remember how we did environment in the ZIO executor, it's really just sort of a variable on, or maybe a stack of variables that are not accessed and provided all the time. So when you interpret that, you could probably erase the cost of the ugliness of that particular implementation as well.
Yeah. So I think the one other thing here that might be particularly interesting for you is, so you notice here when we have the channel, fundamentally the channel has inputs and the channel has outputs. And we've got to put those together into like one operator. And so here we did in this run. But when we do that, we can choose a little bit what order we put them in here. So the way I encoded this here was fundamentally a pull-based encoding, right? It says, give me an upstream, and I'll give you something that you can pull from. But one of the things that I think this makes nice is there's a very symmetrical way that we could implement a push-based stream encoding. So we could just flip this around, and we could say, give me something you want to push to, and I can give you something that you can push to.
And by having, like with one of the drawbacks potentially this executable encoding is that you sort of have to pick one, right? I mean, well, we could do other clever things possibly, but are you saying in the declarative encoding, you can basically get both worlds?
No, I'm just more saying it gives you like a mental model to think about both of those together. Where like, I think previously when we said, well, like, oh, it'd be interesting to explore a push-based stream encoding, like we can say like, yes, but like, I don't know if we really got anything from the pull-based encoding that like really informed what that would look like. Sure, whereas I think here you can kind of see this like natural symmetry that like, this says, give me an upstream and you can pull from it. You could have another version that says, give me a downstream and I'll give you something you can push to.
Okay, that's interesting. Yeah, we have to write a push-based system eventually. And just a couple of final questions here, which is,
yeah, definitely.
Will I only be able to work with Z channel? companion for from iterator, run, drain, etc.
No, so that's kind of a great observation. So generally what we're trying to do when we can is we implement the fundamental operators on channels so that you can use them for your own custom channels, or sometimes we can reuse them across streams and sinks, but that wherever relevant, we re-export them under streams and sinks. So if you're working with a stream, you just do from iterator. You don't really have to know that like internally we call the Z channel operator. You just do the constructor on the stream and you just do the operator on the stream. And the APIs for streams is basically identical to the ZIO 1.0 API. So you don't have to deal with any of this complexity if you don't want to. You just get, one, the performance benefits, two, I think probably more correctness and fewer bugs because we're implementing in terms of this one more fundamental thing. And then if you are kind of a power user, if you want to, you have the ability to drop down to this lower level channel encoding and implement your own channel for your particular customized use case.
Makes sense to me. Well, cool. Maybe one last, just because we mentioned it, just like maybe a high level. What's an intuition for the a use case for the leftovers? Is there a simple example or operator that might make use of those? Is that just for optimization purposes? Is this for
no. So think about so one potential use of sinks is when you're doing like parsing. So you can imagine like the sink is supposed to try to like whatever parse bytes into some user data structure, right? So you're giving it chunks, you're giving it chunks, you're giving it chunks. And in the middle of one of those chunks, it says like, okay, like I'm done decoding, you know, whatever your JSON. I've got some other bytes that like fit into the next JSON, but like I'm only supposed to emit one JSON. Like I found my value, I'm ready to emit, but I got fed some elements that I didn't use. So what are we going to do with those elements? Like we don't want to just throw them away because we need them to like parse the next element. So the inputs give the sink a way to say like, hey, I'm done, but you gave me some stuff I didn't use. Let me give it back to you and you can do something else.
Okay, that makes sense. Awesome. Well, I'll have to take a look at some of the real Z channel operators, as we all do, as everyone should in their lives. Well, thank you, Adam, for walking us through that. That's the septifunctor. It's the crown jewel.
The septifunctor cometh, yeah.
Indeed. But that was super fun. Thanks everybody for joining us this week. And I think we'll be back next week. Are we in London yet? Is it a holiday?
It's literally the Thanksgiving holiday. So we will have to see how we feel about that one. But at one point or another, we will definitely be back to you with more content.
Maybe next Friday or maybe the following Friday. We have functional Scala coming up as well on the 1st and 2nd, or the 2nd and 3rd. So yeah, 2 Fridays is functional Scala. So check that out if you're interested in that. Functionalscala.com probably, or maybe we'll post a link. But anyway, thank you so much, everyone, and until next time.
Take care.
Adios.